Hi, good morning. Today we are going to discuss definition of algebraic and transcendental elements. Now, what do you mean by an algebraic element? An element alpha of an extension field E of a field F is algebraic over F. An element alpha of an extension field E of a field F is algebraic over F if f of alpha equal to 0 for some non-zero f of x belongs to f of x. Okay, if alpha is not algebraic over f, then we call alpha is transcendental over f. Okay, alpha is algebraic over f means f of alpha equal to 0 for some non-zero f of x belongs to f of x. So if you take any element alpha belongs to E, if there exists a polynomial f of x in f of x which satisfies the condition f of alpha equal to 0, then we call alpha is algebraic over f. Otherwise alpha is stated to be transcendental over f. For example, consider root 2 belongs to R and clearly R is an extension field of Q. If you consider the polynomial f of x equal to x square minus 2, then clearly this is a polynomial in Q of x because its coefficients clearly belongs to Q of x. Now what is f of root 2 is equal to 0. Therefore root 2 is algebraic over Q. Okay. Now if you consider the extension field C, in this case if you consider the polynomial x minus root 2, clearly this is a polynomial in R of x because root 2 is not a rational number but root 2 is a real number. Therefore x minus root 2 is a polynomial in R of x. Therefore for this clearly root 2 is a 0. Therefore root 2 is algebraic over R. Similarly root 2 is algebraic over Q. In this case polynomial is x square minus 2. In this case polynomial is x minus root 2. Pi is transcendental over Q because there does not exist any f of x in Q of x such that f of pi equal to 0. Okay, but pi is transcendental over Q. But if you take any polynomial which satisfies for which pi is a root, then clearly its coefficient does not belongs to Q. Therefore pi is transcendental over Q. Now but pi is algebraic over Q because if you consider this polynomial x minus pi in R of x, then clearly f of pi equal to 0. Therefore pi is algebraic over R. So pi is not algebraic over Q, that is pi is transcendental over Q and pi is algebraic over R. Similarly you can prove E is transcendental over Q. Now moving to one problem, show that this is algebraic over Q. Root of 1 plus root 3. If you take alpha is equal to root of 1 plus root 3, to prove alpha is algebraic over Q, we have to find a polynomial f of x in Q of x such that f of alpha equal to 0. So if you take alpha equal to this one, then alpha square equal to this one, alpha square minus 1 equal to this one. But root 3 does not belongs to Q. So we are again squaring it. Then if you consider this polynomial, if you consider the polynomial x raised to 4 minus 2x square minus 2 and clearly each coefficient belongs to Q, therefore this is a polynomial in Q of x and clearly alpha is a 0 of this polynomial. This implies alpha is algebraic over Q. Therefore root of 1 plus root 3 is algebraic over Q. Now moving to definition of algebraic and transcendental number. An element of C that is algebraic over Q is called an algebraic number. Okay. An element of C that is algebraic over Q is called an algebraic number. Transcendental number means an element of C that is transcendental over Q. Give an example. Pi and E are transcendental number. Okay. Algebraic numbers. Each element of Q is a transcendental number because if you take any rational number, if you take any R, if you consider the polynomial x minus R, Clearly, this is a polynomial in Q of x and for which R is a root. So, every element of Q is algebraic over Q. Okay. And pi and E are transcendental over Q. Now show that following are algebraic over Q. 1 plus root 3, root 2 plus root 3, 1 plus root I. For this, first consider 1 plus root 2. Alpha equal to 1 plus root 2, alpha minus 1 equal to root 2, alpha minus 1 whole square equal to 2, and alpha square minus 2 alpha minus 1 equal to 0, and consider the polynomial x square minus 2x minus 1, and clearly this is element in Q of x, and for this alpha is a root, therefore this is algebraic over Q. Now root 2 plus root 3, try it as a homework. Alpha equal to root 2 plus root 3, alpha square equal to this one. Again there is a root 6, so you have to eliminate this. Alpha square minus 5 equal to 2 root 6. Again squaring we get that is equal to 24. And if you consider this polynomial alpha raised to 4 minus 10 alpha square plus 1 equal to 0. If you consider the polynomial x raised to 4 minus 10 x square plus 1, then alpha is a root of this polynomial, therefore this is algebraic over Q. Alpha equal to 1 plus I. Similarly you can do, okay. Now alpha equal to root of 1 plus cube root of 2. Again cube, take cube and we get this one, okay. Now there is one theorem. Let E be an extension field of a field F and alpha belongs to E. Let phi alpha from f of x to E be the evaluation homomorphism of f of x into E such that phi alpha of A equal to A for A belongs to F and phi alpha of x equal to alpha. Then the theorem says that alpha is transcendental over F if and only if phi alpha gives an isomorphism of f of x with the subdomain of E. We have to prove if alpha is transcendental over f, then phi alpha is an isomorphism of f of x with a subdomain of E. Okay, that means that map is 1-1 homomorphism and okay, a subdomain of E, that is if and only phi alpha is a 1-to-1 map. Okay, because phi alpha is already a homomorphism. So to prove this, alpha is transcendental over f if and only phi alpha is a 1-to-1 map. Okay, now moving to the proof. An element alpha is transcendental over f if and only if f of alpha not equal to 0 for all non-zero f of x belongs to f of x. Okay, this is true if and only phi alpha of f of x, because by definition phi alpha of x equal to alpha, and if you consider any polynomial, suppose you consider x square plus 2. What is the meaning? Phi alpha of x square plus phi alpha of 2. But phi alpha of x square is phi alpha of x into phi alpha of x. And phi alpha of x is alpha square plus phi alpha of 2 is 2. So this is actually, if you take f of x as this one, this is equal to f of alpha. So f of alpha you can write as phi alpha of f of x. Therefore, if f of alpha not equal to 0 means phi alpha of f of x not equal to 0 for all non-zero f of x belongs to f of x. That is phi alpha of f of x not equal to 0 for all non-zero f of x. That means kernel of phi alpha is set 0. Kernel of phi alpha is set 0 means phi alpha is a 1-to-1 map. Therefore, phi alpha gives an isomorphism of f of x with the subdomain of E. Now moving to very important definition, and we are proving moving to definition only after proving this theorem. This theorem is also important. I mean the content of the theorem is very important. Okay, so in this case we have discussed characteristic of an element alpha to be transcendental over f. That means this map evaluation homomorphism is 1-to-1 map. Now moving to algebraic. Okay, let E be an extension field of f. An element alpha belongs to E where alpha is algebraic over f. Then this theorem says that there is an irreducible polynomial p of x belongs to f of x such that p of alpha equal to 0. And this irreducible polynomial p of x is uniquely determined up to a constant factor in f and is a polynomial of minimal degree greater than or equal to 1 in f of x having alpha as 0. If f of alpha equal to 0, that is if f of alpha equal to 0, f of x belongs to f of x with f of x not equal to 0, then p of x divides f of x. Okay. While doing this problem, clearly we get a polynomial. Okay. And the theorem says that this polynomial is an irreducible polynomial. Okay. Let E be an extension field of f, alpha belongs to E algebraic over f, then there is an irreducible polynomial p of x belongs to f of x such that p of alpha equals 0. In the case of root 2, we get a polynomial x square minus 2. Clearly this is an irreducible polynomial in Q because we cannot factorize this in Q because only factorization x minus root 2, x plus root 2, but that does not belongs to Q of x. Therefore, this is an irreducible polynomial. There is an irreducible polynomial p of x belongs to f of x such that p of alpha is 0, and this irreducible polynomial p of x is uniquely up to a constant factor in f and is a polynomial of minimal degree greater than or equal to 1 in f of x. That means if there is any polynomial in f of x such that f of alpha equal to 0, then p of x must divide f of x. Okay. Now moving to the proof, this is very important. Listen carefully. Okay. Let phi alpha be an evaluation homomorphism of f of x into E. Clear? Then the kernel of phi alpha, kernel n of phi alpha is set of all f of x belongs to f of x such that phi alpha of f of x equal to 0. That is, n is actually f of x belongs to f of x such that f of alpha equal to 0. Phi alpha of f of x is f of alpha equal to 0. Note that n is an ideal in f of x because kernel of a homomorphism. Okay, this is an ideal. But f is a field. Every ideal in f of x is principal ideal. Therefore, n must be a principal ideal generated by some p of x belongs to f of x. Hence, our n is equal to ideal generated by p of x. Okay. Now, as n is a kernel of phi alpha, ideal generated by p of x consists of those elements in f of x having alpha as 0. Thus, if f of alpha equal to 0 for f of x not equal to 0, then f of x must belongs to ideal generated by p of x. Clear? Kernel consists of all elements having alpha as 0. That means if f of alpha equal to 0 for f of x not equal to 0, then f of x must be in ideal generated by p of x. So, p of x divides f of x. Clearly, p of x is a polynomial of minimal degree greater than or equal to 1 having alpha as 0. And for any other polynomial of same degree as p of x must be of the form a into p of x for some a belongs to f. Okay, if there is any polynomial of same degree as p of x, if degree greater than p of x, then it must be a multiple of p of x. Same degree means it is of the form some constant a into p of x for some a belongs to f. Now we have to prove that p of x is irreducible. Suppose p of x is reducible, that is p of x equal to r of x into s of x in f of x. Then p of x, p of alpha equal to 0 implies r of alpha into s of alpha equal to 0. This implies either r of alpha equal to 0 or s of alpha equal to 0 because since C is a field, is an integral domain. Okay, this contradicts the fact that but we have p of x is a polynomial of minimal degree greater than or equal to 1 such that p of alpha equal to 0. Therefore, p of x is irreducible. Okay. Now, by multiplying a suitable constant in f, we can assume that the coefficient of highest power of x, once again, by multiplying by a suitable constant in f, we can assume that the coefficient of highest power of x appearing in p of x of theorem 29.7 is 1. Such a polynomial having 1 as the coefficient of highest power of x appearing is a monic polynomial. Such a polynomial having 1 as a coefficient of highest power of x appearing is called a monic polynomial. So we get a irreducible polynomial. Suppose we get irreducible polynomial like this, 2x square minus 4. So we can divide throughout by 2, we get x square minus 2. So this polynomial become a polynomial of monic polynomial. Monic polynomial means coefficient of highest power become 1. Okay. Now let E be an extension field of f, and alpha belongs to E be algebraic over f. Okay, thus we for any element algebraic over f we get a irreducible polynomial, and that irreducible polynomial we can make that as a unique monic polynomial. So the unique monic polynomial p of x having the property described in theorem 29.17 is the irreducible polynomial of alpha over f. Okay, and it is denoted by irreducible of alpha over f. And degree of irreducible of alpha over f is called degree of alpha over f, and it is denoted by degree of alpha over f. Degree of this irreducible polynomial is called degree of alpha over f. Now in the case of root 2, we have root 2, irreducible of root 2 over q is x square minus 2, and degree of root 2 over q is 2. Irreducible of root 2 over r is x minus root 2, and degree of root 2 over r is 1. Okay. Now just to recall Einstein's criteria. If p belongs to z be a prime, f of x equal to this one, a not equal to congruent to 0 mod p, ai congruent to 0 mod p for all I less than n with a naught not congruent to 0 mod p square, then f of x is irreducible over q. So using the result, we get clearly x square minus 2 is an irreducible polynomial. Okay, root 2 algebraic over f, and this is an irreducible polynomial in this case we get. Okay, now irreducible of root 2 over r, we have already proved. Irreducible of, we have to find irreducible of this one. Okay, so alpha, and take this one and take this one, and we must prove this is an irreducible polynomial. For this we have to use Eisenstein criteria. Okay, so with the p equal to 2, clearly, okay, all the conditions, this polynomial satisfies all the conditions for Eisenstein criteria, therefore that is an irreducible polynomial. Okay, therefore irreducible of root of 1 plus root 3 over q is x raised to 4 minus 2 x square minus 2, and degree of root 2 of 1 plus root 3 over q is 4. Okay, now next section is simple extensions that we will discuss in